My name is Shantanu Jakate. I've been working on Trakr this semester with my colleague Isaac Lau, and today I'll be discussing more of the mathematical framework and modeling that we're proposing for our system and how we're efficiently managing the data that we're acquiring from our Trakr module. So, to get right into it, a lot of the literature that we have researched this semester focuses on higher order regressions, complex data analysis tasks to basically take in multiple inputs and try to predict the multiple outputs and apply that to a control system. We wanted to simplify the mathematical model behind this and still retain the dynamic qualities of this time-variant system. And so what we're proposing is using a Markov model to represent a black box system, and then using a repository of data and putting it into the system as state vectors. So you'll see behind me we're representing the state vector of the system of our black box here, and I put in just examples of what type of data we can implement. For example, temperature, humidity, location, and number of people in the room. Obviously, we can change the type of data we're putting in and the different data points as we improve the model and get feedback on it. But what we're interested in right now is representing the data as a state vector. So the idea is having an abstracted model of just saying this is our room, and these are all the data points coming out. We're basically able to represent the state the model is in. So if you think about a room, or basically any large occupancy room, we're interested in three states. And so the three states essentially become heating, cooling, and between the two we have steady state. So now the challenge becomes, how do we model these three simplified states for the room? Our first approach, using machine learning or higher order multivariate functions, didn't seem feasible, especially for the scale of our data. So what we wanted to do is implement a Markov chain, Markov model for our data pool. So now that we've established heating, cooling, and steady state are the three states that we're interested in, we can go ahead and start drawing our Markov chain. So now that we have our three states, what we're interested in, rather than a control signal output and feedback into a controller, we're more interested in knowing what state the room is. The way we know this is with the transition probabilities, which we're going to assign a dynamic system to. So for example, at time step I, let's assume the room begins at steady state. There's a probability that the room remains at steady state, so we'll assign this a probability of x, s, s. There's also a probability that the room transitions from steady state to heating and from steady state to cooling. We can assign these similar probabilities depending on what we gain from the system, and essentially assign it according to the nomenclature. So if we finish up this Markov model, you can see that there's only 9 probabilities that we're concerned about. And so from this, we can create a matrix of probability transition states. So now that we have the probabilities such as XS, X, CH. For example, these two probabilities show the transitions from X from the system from steady state back to steady state to heating, and steady state to cooling. So now we can create a 3x3 matrix, so we can say So now that we have a system of our transition probabilities, what we're interested in is, for the next time step, to figure out the transition probabilities for that state. Essentially what we're going to do is create a markup chain where we're keeping the states constant and then changing the probability of the transitions. And now this way we can determine at a certain point of day where the system will lie. And so now we're combining the system and the power of dynamic systems with Markov chains. So in a traditional Markov chain, we see a convergence at a certain probability with respect to time, but that's assuming that the probabilities stay the same, which is not true in the course of a day. For example, a lot of rooms have different heating profiles depending on their natural environment and natural surroundings. For example, in a room with lots of glass or not proper insulation, we might see a peak similar to how the sun heats the room. When we apply this type of input to the system, we're going to see the probabilities of transitions shift. And so it's really important that we model these transitions effectively. In our computation that we're proposing, we don't have to make delta t, delta t doesn't have to incorporate a stiff matrix. This reduces a lot of the computation time and allows us to use solvers that are not as computationally expensive. So from what we can do from this state is basically create another black box system. So I'm going to talk a bit about the implementation that we're planning for our system and how we can utilize this Markov chain and the dynamic probabilities to our advantage. So for computational costs, we're thinking about using delta t to be about 30 minutes. So what this will allow us to do is basically divide a 24-hour day into 30-minute segments and create basically a close to 48 state vectors for the entire day. And so for example, let's say we have a class at 9:30 a.m., 3007. So what we can say is we have a state vector, this is at 9:30 a.m. So for example, let's assume at state 0 at 9:30 a.m., the room is not as hot because it's early in the day, there's not many people in it, and there's not much air conditioning going on or any perturbations to the system. However, with our Markov chain model, what we're estimating in the next half hour, we're estimating that there's going to be addition of different variables such as heating of the outside. Number of people will increase in the room. For example, we have class in there. And perhaps the humidity will also go down because the room is now going to go to steady state with the outside environment. So now we have all these different perturbations in the system, but we're already predicting that using our Markov chain. So now we're in our non-stiff matrix. What we can do is go to a stiff matrix and basically see the convergence of our system at that particular point. So now we're interested in the convergence of our system. And so if we can predict in that state where the Markov chain will converge as system S1, then we can basically assign a probability to our control system and say this is a very high likelihood that the room is going to be in a heating period. For example, we might see things in our Markov chain, for example, a convergence at 64% likely that the room will be in a heating state at S1. So what we can do with this feedback is say heating is our winner from our system, and then feed that to the existing building management systems to now turn on the air conditioning. What we can now do, which is pretty interesting with the Markov chain, is now implement that back into our original matrix and say that we're cooling the system, that the system already knows that it's going to do this cooling, and then implement it back into our controller so that perhaps at system 2, we will be in a cooling period. For example, at system 2, we might see things as people leaving the room, humidity increasing, and a cooling period because now the control system is turned on. And so now this is a dynamic model incorporating a time variant system into a Markov chain. So now that we've introduced our Markov system and our model, I'd like to go through basically an example of how the system would run and what we're expecting our framework to look like. So let's take the example of having class 3007 Tuesdays and Thursdays at 9:30 a.m. So what we're going to do is represent 3 different states, and I'll walk you through how the system could potentially converge onto a control feedback and basically actuate the control system that's already in place. So for example, let's represent this state vector, state 0, as a 9:30 a.m. We'll set our delta t to be quite large so that we can have a non-stiff computation. So in one transition, as you can imagine, there's a lot of inputs that are being put, a lot of inputs into the system. For example, the number of people in the room is increasing. The dynamics of the room with the door opening and closing is also changing. And then the different heating and cooling elements of the outside weather is also changing. As the sun has more time to heat up the room temperature may increase. And especially as the number of people in the room increase, the heating factor, as you consider people as heat sinks, the temperature of the room will increase. So what we can say is, if we take the Markov chain at S1, we can basically create a plot that will say, for example, we will write steady state here, heating here, and cooling here. So we want to basically know the probability of being at each state. And so what we can do is take our dynamic data, our state vector, apply our matrix at that state, at that position of time, and say, hey, our graph looks like this. So that means we're most likely going to converge at a heating state. So at state S1, we're expecting to be in a heating period. So now this is really useful information for our controller. So what we're going to say, we're going to send a heating signal to our controller. And controllers are already prevalent, very extensive research, especially with PID control. So we're not looking to actually change the control models in the sense that create a novel controller, but we're interested in how we can send that data effectively. So now that we've sent the heating state signal to the controller knows that it has to apply a cooling function, in this case turn on the air conditioning or increase the air conditioning in the room. What we can do is go back into our matrix Markov model and say, if we already know that the system is planning on implementing a controller, it's most likely going to change the matrix somehow and the transition probabilities. And now our plot's going to look a bit different. So if we have the same steady state, heating and cooling, we might see a convergence around cooling, so that we can say it's most likely the system at S2 will be converged at cooling. So we can expect around 10:30 a.m. the system will be in a cooling state. And so now we can basically represent the system as a dynamic model with a Markov chain, and this is an example of an implementation of what our system would do. So now that we've established the fundamentals of our project, we'd like to talk a bit about the scope of AI and ML methods for improving the scope of our project and making it more human-centric. So the idea behind human-centric building management systems and HVAC systems is that we obtain nominal feedback. And so the assumption that, for example, temperature set point, and I think a lot of the fallacies we want to tackle with this project is that set point does not equal comfort. I think everyone's been familiar with that room that's set at the exact perfect temperature, but is still too uncomfortable. So now the question is, how do we tackle things like this? And so what we want to do is incorporate a learning heuristic for our system. So for example, if we go back to our state representation of the system, what we can say is, for example, we have a state vector at a certain point and say the system will make a guess in a training period of what the system thinks the user will like. And we'll say, okay, well, user has, from historic data, said they prefer 68 degrees Fahrenheit. Comfortable temperature keeps you awake. But let me see what happens if I lower the temperature to 65 degrees. And so now what we can do is say, okay, we have a state vector, but I'm going to put a cold tag on it. So I'm going to say this is a cold state vector. Now we will run this in our markup chain throughout the day, and what we'll do is get feedback from users, most likely from buttons on our module, either in the form of smiley face, happy face, or neutral face. Obviously, people who prefer to put neutral face won't put it up there, but for example, in this case, we've moved the temperature down significantly. And let's say we get a string of repeated sad faces. That's not good. So now the system will take this feedback and say, okay, I pushed the system too far down to 65, and it's not really, people aren't really liking it. So on the other side, we can try the same thing and say, what if we had a hot temperature for time I? And so it might assign a temperature above, for example, maybe 71 degrees, and for that one, we might get a lot of happy faces. And so now the system will say, okay, we can repeat that process and say, we can repeat that process and until we get the perfect temperature, and then we can associate people's comfort levels with the optimal set point. And so it becomes a different paradigm. Rather than moving from set point to comfort, it becomes comfort to set point, and it's a human-centric approach to HVAC systems. In the scope of learning heuristics, what we also thinking of implementing is a bandit algorithm or a cumulative regret algorithm for training our model. One of the fallacies that we see in a lot of the literature is infinite training periods, and that the system is always improving. If the system is always improving, it's really hard to actually record the perturbations in the sense that it becomes difficult to converge. And at a certain point, it doesn't make sense to keep training the system. So for example, let's say we have a 10-week class here at MIT. If your system keeps training all the way to the end of the class, you have no actual functional use from a learning system. So if you incorporate a max training period where the system has a certain amount of time to train, then it can actually prioritize different states and different temperatures and then change the scale, for example, so it doesn't test 69.5, 69.6, 69.7, it would test more discrete values, and so by the end of the training period, it's localized to a good solution that is actually comfortable to people rather than to the global optimal solution. So this is an example of how we would implement learning heuristics and different frameworks to make our product more human-centric.